Now, we've talked a lot about the properties of analytic Fourier transforms, and this is really useful because oftentimes you can approximate a physical situation using these analytic functions, and you can manipulate them using the theorems, and it can be really powerful and useful. But sometimes you have a pile of numerical data, and it's a table of data. You can plot it in the time domain or in the spatial domain, but you might want to know what its frequency components are. In other words, you might want to take a Fourier transform of some data. And that means taking a Fourier transform numerically. Now, computers are fantastic at doing this, and there are lots of packages that allow you to take very fast Fourier transforms. Indeed, the algorithm normally used is called the FFT, which stands for the fast Fourier transform. But before we take fast Fourier transforms, we have to understand what it means to sample some function of time or space. Because if you sample it incorrectly, you're going to get silly answers. So let's start with a sine wave that we're sampling at a frequency of 1 Hertz and see what happens. So here's our yellow sine wave at 1 Hertz, and we sample it, in this example, every 2 seconds, so the sampling frequency is half a Hertz. And so the blue dots here are the samples. If I join the blue dots together here, I get a straight line. So I've completely missed the fact that I have a 1 Hertz sine wave. If I just look at these samples, I think, oh, I've got some function which is a constant and has a constant value of 1, missing the fact that I have some underlying oscillation. So you might say, well, okay, fine, so we need to sample a bit faster. Well, let's try increasing our sampling rate and see what happens. So a little bit quicker, let's say go up to 2/3 of a Hertz. Now I have something that oscillates at least, so I recognize that I have some signal that's varying between 1 and -1, but it's still wrong. So here, the frequency is 1 Hertz, but I look at this, and this periodic function now appears to have a frequency of 1/3 of a Hertz, has a period of 3 seconds. So I could, if I, instead of having a yellow 1 Hertz sine wave here, if I had another sine wave that was 1/3 of a Hertz, I could be sampling this and picking up that frequency. So this is still not right. And if you look also here, the frequency difference between the 1 Hertz sine wave and the sampling frequency is dictating the frequency of this false signal here. Let's increase the sampling rate a little more. Let's increase it to 1 Hertz. At 1 Hertz, we have the same problem that we started with, which is we think we have a straight line because it's picking out all the peaks of the sine wave. Let's increase it to 1.5 Hertz. So there we have 1.5 Hertz about here. Now here I've picked out a frequency of half a Hertz, because we have this blue curve, this blue line now that we're joining the dots with is periodic with period of 2 seconds. So it's half a Hertz. Again, it's the frequency difference between the sample rate and the real frequency that we have. Finally, only when we get to a sampling rate of 2 Hertz, which is twice the frequency we have here, do I get a sensible answer. This is the first time I pick up the correct frequency. And if I increase the sampling rate now, I might get some additional sort of beating patterns here, but I always pick up the frequency of 2 Hertz. And as I increase the sampling rate, I get a closer and closer approximation to the real curve that I started with. So this tells us something really important, that there is something magical that happens at this sampling frequency of 2 Hertz, which is twice the frequency of our signal. And so what this tells us is that to pick out a frequency f, you need to sample at least 2f. Or to say that backwards, for a sampling frequency f of s, the highest frequency you can correctly identify is half of f of s. And this highest frequency, which is half the sampling frequency, is known as the Nyquist frequency. Now, if you consider that any function can be composed as an integral or sum over harmonic functions like this, what it tells you, if you have some signal that has some range of frequencies, and let's consider audio signals. The human ear can hear frequencies up to about 20,000 Hertz, and so in order to capture an audio signal and reproduce it correctly, we need to sample that audio signal at least twice 20,000 Hertz, so 40 kilohertz. And audio signals generally are, for most audio, is sampled at 44.1 kilohertz, which is a choice that they made some time ago when they were deciding on the standard for the compact disc. And this allows you to capture the full range of frequencies that the human ear might be able to hear. Okay, now we've talked a little about sampling. Let's get some numerical data and take the Fourier transform and see what we can find. We'll start with some data. In this case, it'll be acoustic data from a piano that sounds like this. So it's a simple piano tone. If we plot the time series of this data, we see something like this. So this amplitude here is the pressure in the sound wave as measured with a microphone, and we plot it as a function of time. We see the sound goes for about 3.5 seconds. The data is sampled at 22,050 Hertz. So the maximum frequency, i.e. the Nyquist frequency that can be represented in this data, is 11,025 Hertz. There are nearly 80,000 points in this data, and this is the reason why you can't see the wiggling sort of waves in this data. It just looks like a sort of solid block. Now, normally audio data is sampled at a higher frequency of 44.1 kilohertz, such that the Nyquist frequency is above the range of the human ear. In this case, that won't be true, but as you'll see, the frequencies in this sound are low enough that actually doesn't matter so much. So there's our data, and we can use some numerical package like Mathematica to take a Fourier transform and find out what frequencies we have in this data. So here's the Fourier transform. This is a real part and an imaginary part. We have real and imaginary parts because the function is neither odd nor even, so we get a bit of both. The data here is plotted from negative to positive, the Nyquist frequency. So we've got minus the Nyquist frequency and positive the Nyquist frequency, and that's the maximum range of data that is sensible to plot, because we can't understand frequencies that are beyond the Nyquist frequency. The largest frequency component we can see here occurs at 523 Hertz, which is C5. And we can see it has peaks in both the real and the imaginary part. Now, the details of how to get this result will be in a separate video that runs through the Mathematica notebook I use to generate this data. Normally, though, when we think of a frequency spectrum, we don't look at real and imaginary parts. We just look at the power in each frequency component. So to do that, we take the Fourier transform, which is these two things combined, the real and the imaginary parts, we square it and plot it on log scale like this. Now, we know the square of the Fourier transform is proportional to the energy. This is what Parsifal's theorem tells us. And so what this graph is showing us is the energy at each frequency component in this spectrum. So we can see there's more energy at this frequency than there is at this frequency. It's customary to plot this on a log scale, or 10 times the log of the square. And this is because the difference between the peak and the bottom here can be really enormous. So for example here, from here up to here is a difference of 50 or more, 60 on this scale. And so that is 6 orders of magnitude difference between the peak here and the bottom here. And if you plot that on a linear scale, it's pretty hard to see. The 10 times the log here is known as a decibel scale. So if you hear decibels, this is what decibel is. It's 10 times the log of the power. Now if you take this squared out to the front here, it's actually 20 times the log. That's an aside. And this spectral density plot is what people often refer to as a spectrum. It shows the energy at each frequency and just completely ignores the phase. It's just the energy available at each frequency.